with origin stories. So we know about Spider-Man, Superman, and recently Wonder Woman. So as one of our digital communications...
Not as good looking as Gal Gadot.
One of our digital communications superheroes, I wanted to ask you about your origin story, especially as it pertains to USC. Because, of course, everyone knows that one of the reasons why you chose to do your PhD at USC is that we were, very accommodating about you being here part-time.
You weren't born yet.
It's true. It's true. I feel awkward with the whole I-we thing, but I hope you get the big idea here. So I once incorrectly attributed your PhD advisor to be Saul Galom. I now know that your PhD advisor was Gregory Young, who was actually the first PhD in electrical engineering at USC. Correct. And stayed on to be a faculty member. And so I was hoping you could tell us a little bit about how you and Dr. Young got connected and what your interaction was. Presumably you didn't Skype to have meetings about your PhD research.
Well, Greg Young was a very bright fellow. He was also a very sloppy guy. He went around, his shirt tails were all sticking out, and he loved to go have a beer at the local pub. I guess there were pubs then near campus. And yes, he was the first PhD. He was, in those days, USC professors spent 3 days on campus and 2 days working for Hughes. And most of the students were too. Well, I was at JPL, a little different. He was an excellent teacher. The courses weren't at the quality that you teach nowadays because people didn't really understand Shannon. I had to learn that on my own. But my biggest problem was just corralling him. I'd have to go have a beer with him in order to tell him what I was doing. Which was certainly not the quality of the work that I did later after my degree. But he was a very fine fellow, and I enjoyed it. In fact, I had a committee that was very interesting. There was Greg Young, Bob McMillan, who was a good teacher, didn't do much research, but he loved to give doctoral exams. He would prepare tricky problems. And then the third was Nasser Nahi, who was a distinguished control theorist. Sadly died very young on a trip on an airplane flight back from Iran, where he had gone to visit his father before the revolution. Of the three, I would say the only distinguished researcher was Nahi. But Macmillan gave me such a bad time, I was sure I'd failed. And then I came back 2 days later. I didn't want to even think about it for 2 days. And Nasser Nahi told me that was the best exam we ever got.
That's fantastic. So, how would you say that your USC experience influenced how you were as a PhD advisor?
How I was?
How did your PhD experience at USC influence how you interacted with your students at UCLA?
Well, when I went to UCLA, that was the height of my learning experience. The best way, and I'm sure every faculty member here will agree with me, the best way to really understand a subject is to teach it. And with Balakrishnan, the department was already pretty well established in communication and control. And I had, again, students who spent the day at Hughes or TRW or JPL and would come late in the afternoon. And I learned a lot. And that's also how I got the idea for the algorithm. Well, you can probably share, can't you?
It won't record.
Oh,
No, yeah.
oh. Oh, it's one
The
microphone.
battery's dead on the. So, can everyone hear me?
Yeah.
So, again, I want to echo Oakley's comments and thank you for coming and giving a wonderful talk. It's an honor and a pleasure to participate in this. And also, I'd like to thank all of the students and faculty for showing up. I'm happy to see we're violating the fire code here, and you deserve no less. So, the one question I wanted to ask you about relates to technology evolution and your research and how those two things sort of dovetail together. So when we look back, someone from my generation looks back, it's pretty obvious that the Viterbi algorithm was a natural marriage with VLSI technology. When did that become apparent to you? And so from the time, can you kind of trace your discovery of the Viterbi algorithm all the way through to the first full integrated circuit implementation of it, from software, hardware,
Let's see,
prototyping, et cetera?
I wrote the paper in '66. It was published in '67. The Moore's law had just been hypothesized by Gordon Moore in a paper in a trade journal. At the time, certainly in '66, '67, we had no clue. By '69, doing simulations on JPL computers with a JPL engineer, Jerry Heller, we found that even a relatively short code, one that had 6 stages, we could gain something on the order of 5 dB relative to uncoded, which was considerably more. And part of that was because we could use soft decisions, whereas just about all the other techniques, both algebraic coding and sequential decoding, needed to operate on binary and therefore hard decisions. But the first implementation, so still it was pretty theoretical, although, with JPL involved, they were thinking ahead to the space program. The first implementation was actually, I believe, in 1970. 73 or 74. And I think there was some software programs written for Naval Electronics Lab in San Diego. But the first hardware was at a reasonably high speed. That in those days was probably on the order of maybe 100 kilobits per second, was for JPL, and that was in the mid-70s. And then, and that was a box about, a rack-mountable, 19-inch wide, about 5 inches high. And then we did another implementation a couple of years later for the Army satellite communication. And that's the first time it was used in transmitting fairly high data rates across the Atlantic Pacific. And that was operating at 10 megabits per second, so it was getting up there. And that took a somewhat larger box. And then I'd forgotten whether it was Army or Air Force wanted 50 megabits per second, so we stacked 5 of them one on top of the other and got them in a rack. But the Moore's law phenomenon was grinding away, and by 1986 we could do all that at the speed on a chip. And if you go to the museum in the next building, you'll find one of the original 10 megabits, kind of big, and then there's a chip. And now, of course, you can't even see it.
So do you have any advice for our students and younger faculty on how you sort of spot these trends? I mean, when did it become apparent to you that you would be able to, ride that Moore's Law wave and do all kinds of what would be considered in the 60s
Well,
esoteric processing?
Actually, that first box already was using integration. We had about 100 gates on a chip. And that generated the add, compare, select circuit, and we needed 64 of those, and then all the support. So there were about 300 circuit chips altogether. The competition had, because it was in response, we proposed a design in response to a request for proposal from the, I guess the Army Satellite Communication Agency, Fort Monmouth. And the competition's design was about 1,000 chips because they didn't have the integration that we had. So already the first real implementation had a very small amount of integration. By the late 80s, that had increased 1,000-fold. And so it became pretty obvious. Yeah, but I would say almost from the beginning, we realized that we would need some degree of integration. There were several technologies around, and they all seem laughable at this point. Now, how do you spot it? Well, at this point, it seems to be more software than hardware. And it's more application-oriented. And where is the future? I think it's in health sciences and biology. And a lot of electrical engineering departments are converting themselves into bioelectrical engineering departments.
So one of the things that you commented on in terms of the early days of USC, and I think we probably saw this at UCLA as well, is that there was tight connection or interaction between faculty and industry. People had part-time positions, they did a lot of consulting. And so one of the questions we had was, how did your consulting influence your academic work? And what kind of advice would you give to the rest of us in terms of how to artfully merge those different sides? Because I think it's actually possible now to get a PhD or be an academic without necessarily interacting with industry at all.
Yeah, well, in the first decade after my PhD, when I was full-time at UCLA, I would consult at JPL pretty regularly. And then a few companies, I remember Magnavox in those days was very strong on spread spectrum, Motorola, and even McDonnell Douglas. And all of that, yes, did indeed influence not only my research, but even my teaching, because you could see where it was all going.
So can you think of a particular problem or example that you learned about through your industry collaboration that sets you off on a new direction?
Well, certainly, I felt strongly in those days that there was a natural mutual support between information theory and satellites. It was satellite communication that first made error-correcting coding useful, because you had these huge distances, planetary distances, and therefore a very, very weak signal. And by being able to save that 6 dB, you could, with 6 dB, you could double the range, or you could reduce the lift weight by as much as a factor of 4. And so, yes, a lot of my research was very much influenced by the space program.
So another big question we had was, and both Keith and I had this jointly, was what propelled you to decide that you were going to actually leave UCLA and jump in with both feet into Linkabit?
Well, I didn't jump immediately. It was 3 years after we founded it that I mean, it meant more than jump. We also had to change city. Because by then, Erwin Jacobs had it, he had left UCSD long before, almost from the beginning, I think, 1970. He devoted full time. And so I was commuting once a week, that 125 miles down I-5. By that time, we had by 1973, we had a really large company, 25 people. And it was big in those days for a startup. And we had no venture capital. So it was hand to mouth. And I felt both excited and also I felt it was the right thing to do to go support my colleagues.
So was it easy to convince your family that the move was the thing to do?
It didn't take too much convincing, although I will say Erna said, well, we're going to a small town. Then we went back a couple of times and the traffic was horrendous. And said, well, that wasn't such a bad idea after all.
So in your talk, you didn't name the system Omnitrax, but you sort of alluded to it when you were talking about this secondary system. So
Yeah.
can you expand on that a little bit and sort of maybe, I know there's a connection to CDMA Cellular coming out of this with discussions with Klein-Gilhausen and so forth. Can you explain what it means what the secondary system means a little bit more and a little bit about Omnitrax and how that evolved into the ideas behind IS-95 and 3G?
Very good point. It was a major step for a number of reasons, including, well, I'll come to it. The idea was to provide a network of, or to support a network of transportation vehicles, trucks, traveling all over the United States and all over North America, actually. And those were the days before cell phones existed, but only in cities, pretty much. And there were wide expanses where there wasn't any. And it was pretty rough on the truck drivers. They'd have to stop at a truck stop and connect up with their dispatcher at least once a day, and it lost them an hour's worth of labor. There were some people that were talking about launching satellites to provide two-way communication, well, position, location, and communication to trucks. When a JPL graduate came to us with the idea, but it was very, very, very rough, would never have worked. But he did give us a $10,000 contract to develop the idea further. So we came up with an approach that used existing satellites rather than having to launch new ones. The problem with and there was a glut of satellites in the, I'm talking about the early 80s or the mid 80s. And there was a glut because people were thinking in terms of direct TV, and Rupert Murdoch, in fact, had made a semi-commitment to provide a network which is like what Sky TV is today. And then he pulled out at the last moment. And so as a result, there had been a number of satellites launched, and they weren't really being used that much. But they were designated for fixed usage. In other words, you had to have both the hub and, naturally the hub, but also all the other users, like cable television stations. They would receive a signal from the broadcasting studio and then retransmit it on cable. But somebody noticed a footnote in the regulations that said that it could be used as a secondary service for mobile, provided, but only as a secondary service, where, as I said, it meant that you could not interfere with the primary users, and which could be in a different satellite, but it could be the arc separation was such that it would your signal could bleed over into theirs and vice versa. And as I said, you could not interfere with them so by spreading, they wouldn't even notice you. You'd be just a dB or so above the noise. And vice versa, if they interfered with you, you had no choice. You had to take it. But by spreading, they would look like a jammer, but would be spread out. And so, again, they would be just a little bit above the white noise, especially with satellites where the distance is so great. So the thermal and atmospheric noise was a dominant one. So we were able to demonstrate it to the FCC. That took about a year. They did give us a license for 600 trucks. And then after a year, they raised it after we passed all their requirements, and they were not able to detect our signals. They gave us 20,000 and then 40,000. Eventually, I think there was something like 300,000 trucks in North America using it. Now there's far fewer because of cell phones. And almost exactly 25 years after the initiation of the service in 1988, so that would make it 2013, they sold the division to a private equity firm. I was long gone, so I had nothing to do with it, but it was kind of interesting that it happened a quarter of a century. So any technology is going to become obsolete in a quarter of a century.
So how do you go from low probability of detection spread spectrum signals to multi-user systems and CDMA and cell phones?
Well, okay. One of our engineers came in one day and said, this would be great for cellular use. And this was the days when the FCC was just considering the transition to digital and had pretty much already made up its mind. Well, when I say the FCC, it was the carriers and the manufacturers had already agreed on a TDMA system, time division, multiple access. And so we came along and said we can do better. First, my first reaction was we can't do it because of the near-far problem. And Klein Gilhausen, who was a blessed memory, who was a very clever engineer, said, no, it's a two-way system we can power control. And so that happened we got started with that in 1988 or 89. And then it took at least 2 years to convince anybody that it could possibly work. And that was in 91. We finally got approval by the carriers and the manufacturers. But the condition of the carriers were the old Bell, what they called the baby bells, and as well as some of the other players. They had something called it still exists, Cellular Telecommunication Industry Association. And they gave us the go-ahead to try and, on the condition that we had two manufacturers for infrastructure. And they were, the two logical ones were Motorola and AT&T. And after a lot of struggles, we got them going. And the only way we could get them going was to build it all ourselves first.
So I wanted to ask about that because we understand that the first CDMA demo had some excitement.
Oh, well, the demo was in order to convince the CTIA, and that almost didn't work until the last moment. That was probably in 1989. And at that point, people started getting, yeah, and that was one of those heart-stopping moments. And after that worked, then we got a couple of players, was then called Pacific Telesis, which is now a small part of Verizon. In fact, it was Verizon really who, the various portions that got together and became Verizon that sponsored or supported our approach, or at least gave us a chance. And in 1993, I believe, 1991, they voted to consider, after the CDMA standard had been developed but not yet voted on. They agreed to let it be voted on, and it was voted on in 18 months later. That was 93. And it became a standard. But if we had relied on the U.S. carriers, it would not have survived because they already had a well-established analog network. And they slow-rolled it for good reason. It was more expensive and all. So how did it get off the ground? Through South Korea. And South Korea voted it as the only digital standard, the only standard, because they had no analog telephony to speak of. And their system started operating in 96, and until the year 2000, in the United States, we had fewer users than the South Koreans. By that time, we got up to about, I think, somewhere in the tens of millions. And then it blossomed.
Yeah, just a personal note. I spent my summer of 1989 at Qualcomm before I came to grad school. And so while this was going on, there were only, I think there were under 300 employees or so around that time. So, and 150 engineers or something. So they were taking on the world. There was a feeling there that they were taking on the entire world, redesigning the cellular system, and they were just this tiny little company in San Diego. It was a really great environment.
And we had to give not only demonstrations, but participate in debates all over the world in order to keep it going.
Sure. So, what, oh, do you want to take questions from the audience? Or? Yeah, sure.
There's been a lot of lectures over in physics about quantum bits. When quantum bits get going, how's that going to change things?
Well, it'll probably throw the cryptographic world into a tizzy more than anything that we communicators do.
So I had a question on Qualcomm. There were 7 founders of Qualcomm. Is that right?
I think so, yes.
So I mean, usually people think of it as you and Irwin Jacobs. Can you tell us a little bit about the early team and
Well,
the
the
different
7
people you
founders
had?
all came out of Linkabit.
Right.
So
So can you tell us a little bit about the sort of team that you put together and the different talents and characteristics that they had that you think maybe was important for the success of
well, all but
Qualcomm?
2 were very good engineers. No, not the two. No, I'm not talking about Erwin and myself. We were very good engineers too. But no, they were good people. I mean, we had two administrative folks, a manager with considerable background and expertise, and a chief financial officer. There were two, and the other five were engineers. And it was collaborative. And we had collaborated for some years. I think of the 5 engineers, they'd all started within the first couple of years of Linkabit.
So I guess I should have stated this also earlier, but I suspect the only reason why I got an academic job, or actually had a PhD thesis, was largely due to the work that you had done. My PhD was on multi-user detection, and after coming to USC, I think for the first maybe 13 or 14 years, every one of my PhD students went through Qualcomm one way or another, either as an intern.
I remember Keith very well, but he wasn't your student.
No, he wasn't.
I might have been.
I feel like we have a lot to teach each other, but I'll say it's mutual. So I wanted to end with a bit of a philosophical question, which is, as you said so elegantly in your talk, a lot of the work that you've done has been exploring how we deal with memory in systems, channels, codes, etc. And I'm wondering, as this individual who's done so much on dealing with memory, if that in any way influenced how you wrote your memoirs. Like, do you feel that you have a different perspective on memory than someone else?
Well, I've lost most of my memories.
But do you think as an engineer you wrote your memoirs differently than somebody who was a non-engineer? Or how you approached the research?
You're talking about memory from a sociological viewpoint rather than a technological.
Well, I'm going to remind you of what you said about engineering and health. And I think one of the things that we're seeing is that our ability as engineers to influence either medicine or practice or preventive health is becoming larger and larger. And it's not just through materials, et cetera. It's also through algorithms, et cetera. And so I think there actually is a connection between engineered memory and, say, human memory.
Well, there's no question that whether it's machine learning, artificial intelligence, or a better understanding of how the brain works, that will have very significant breakthroughs in this century. But another aid to memory is this little device. You go to a search engine. I won't name any particular companies, but whichever your favorite search engine is, and you can augment. You can fill in all the things that you've completely forgotten, all the names, and that's a big help.
Great. Well, Andy, thank you so much for sharing your experiences with us. It's been really an illuminating experience, and we're grateful to have the chance to talk to you about the various influences you're in your life. And I want to echo Keith. I think our crowd has
I'm
actually
overwhelmed
grown.
by the audience.
Yeah, no, it's so great to see so many students and faculty here to join us in this conversation. So will you please join me in thanking Andy one more time?
Thank you so much.